Again, we're going to pretend positive to negative current flow, just to make it simple. Now, we want to reverse the direction of the current flow in the same coil. How will we do that? Simple. We would make this one negative, which would be that one, because that's the negative rail. And we want this one to be positive, so it's now these two. So that's energizing the same coil the other way around. So now that's positive and that's negative. And essentially, using a combination of these 6 switches, you can do anything you want. You can, any coil you want to energize in any direction. So I'll give you another example. We want to energize this coil, these 2 coils. We want that to be positive and that to be negative, and then we want to reverse it. So we go positive. Let me think about it. Negative. Yeah, so these 2, that one and that one. So now negative rail is connected up here, and positive rail is connected up here. So you've got positive, negative, and you want to reverse them. So it's like that to that. That will now reverse the current flow in that coil. See what I mean? Now, we want to create a rotating magnetic field. So how do we do that? What we want to do is, I have to think about this because it always does my head in. Right, let's see if I can do this off the top of my head. Let's start with these 2. We switch these 2 on, which means we've got negative and positive. These 2 are energized. This is negative and positive, generating a magnetic field here, right? Then we're going to go switch this one off and then this one on. Okay, so that one's still positive, and now this one's negative. So it's gone from these 2 to these 2. Same direction of current flow. These 2 to these 2. Then we're going to go, that one is going to come on. And then we've got now positive, negative. Now it's this one on. So we've gone from that one to that one to that one. So we went that one to that one to that one. What do you think is going to happen next? Let's have a look. What happens next is this stays on, and then now this one comes on. Ready? So now that's negative, green is negative, and that's positive. So you've now gone back to this one being on again. So you've gone doosh, 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 back to the start. But what you've done now is you've reversed. So you've got this coil on now, but you've now reversed the polarity. So that's now positive, and that one's now negative. Now let's continue. This one comes on next. Oh, my fingers are too short. This one's on next, right? Put my thumb there, my finger there. So you've got, it doesn't work so my hand covers it up. Let's try that. Negative, and now this one is positive. So you've gone, again, doosh, doosh. Now you're going to come to this one, which is now negative and positive. So it's going from there. We'll do it again. Doosh, doosh, doosh. Like that. I'll do it with my fingers. There. 2, 3. And what happens after that? That one goes off and this one comes back on. And that's our 6 steps. We're back to where we started. If we continue to run those 6 steps, then we're going to go 1, 2, 3, 1, 2, 3. So I've just realised my arms can't stretch that far. You're going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I even find that hard to understand now. So all you've got to remember is we're going to step it like that. 1, 1, 2, 3, 1. Sorry, let's try that again. We're going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and back to the start again. So that's what we're going to do. Continue that pattern, and that will give you your rotating magnetic field. If you want to reverse the direction, it's the reverse. It's this one. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Okay, so it's exactly the same in reverse. Hopefully that makes sense. That will generate you a rotating magnetic field, along with pulse width modulation if you want to create a sine wave. Hopefully that makes sense. AC, I mean, it does the job of both. It'll regen and it will act as a snubber. Any transients in any direction will be, again, rectified onto the DC, back onto the DC bus like this. So we already looked at that in the last video, actually. And these are the 3 red capacitors, 220 nanofarads with the little 10 kilo ohm resistors. These 3, okay, that's them. So that's your driver circuit. These are your 10 ohm resistors that I was talking about, with your diodes. So what these diodes will do, as the chip turns on the gate, the diode is in reverse bias mode, so it won't pass any current. The switch on of the gate will be handled via this resistor, so it will limit the amount of current that can be passed into this gate. If you get too much, you'll get ring in, and you could even blow the IR2110s up quite badly. They'll just short circuit. That's what these tend to do. Easy to diagnose because the chip just gets red hot. Stick your finger across them. Oh, that one's red hot. Look at that. So don't worry too much about that. So if you get a gate resistance that's too high, as I showed you earlier with the igbts, if it's too high, this will take too long to charge. If it's too low, it will charge too quickly, cause lots of ringing, and draw too much current from these and blow these up. Now, so that's when it switches on, it uses this resistor. Now when it switches off, this will then become forward biased, which will allow the current to flow back very quickly. So it'll switch off nice and fast, which is what you want. Hello! Right, 4 minutes left of this video, so what can we tell you about the driver circuitry? Got your high N, which is going to fire your high side, and your low N, when that goes high, that's going to fire your low side FET. And as we said earlier, you can't have both on together because you generate a short circuit and not good. So the whole point of the circuit is to give you good quality switching, and also to be able to form a bootstrap circuitry to fire your high side. So firing the low side is quite easy. It just gives it supplies that gate there with whatever this voltage is, so plus 12 volt in this instance, and that's that thing switched on. Now you could probably just do that with the Arduino, but the high side is a lot more complicated. So the high side, basically to switch on a FET, switch on a MOSFET or an IGBT gate, you need to have the voltage of this one between 5 and 20 volts above your source here. So 5 to 20 volt above here. But how do you get 5 to 20 volt above here? Because this is at about 150 volts, isn't it? Let's assume that's 300 volts there. That's going to be 150 volts. So what the IR2110 does, it's quite clever, is when you fire the low side, this happens. It draws current through this diode, through the capacitors, both of those capacitors there, C1 and C2, because this is now conducting. Okay, now obviously this is also on. So because that's come on, then this has now happened. Current's flowing through here. So you've got those capacitors charged up to a diode drop below 12 volts, so 11.5 volts there. So what that will do is that will use that on the next pulse. When you now want to pulse the high side, so when you activate high N, what happens is the high out is activated, and it takes the source from here into pin 5, but it also adds, sorry, this is now not conducting, it also adds from pin VB the voltage from these capacitors, and along with some clever circuitry in here which I'm not going to go into, it will now add that to, it'll add it to your source voltage. So whatever the voltage is here, say that's about 150 volts, then that will supply this gate with 164 volts. What am I talking about? Yeah, about 14 volts above, so 162 volts. So at the end of the day, this gate here has got 12 volts above what its source voltage is, and that's exactly how it works. Otherwise you just cannot fire a high side FET without using P-type doping. So these are both N-type. The reason we don't use P-types is because it's just hard to get hold of, expensive, and all sorts of nasties. So hopefully that's the driver circuit sorted out for you. These are just decoupling capacitors here. These just keep the logic supply voltage very clean with minimal amount of noise. So the 5 volts here is just dictating that you want 5 volt logic signals going in. Not exactly that, but anyway, video's ended. See you next week, guys.